Thank you, Amber, and welcome everybody to today's webinar, Learn to Use RISAFoundation. As Amber mentioned, my name is Debbie Penko, and we'll be going through all the steps to figure out all the different pieces of RISAFoundation. Kind of start out here, let's talk about the version we'll be using. So we're going to be using the current version we have, which is version 5.0 of RISAFoundation. This is compatible with the other programs that we have. So RISA-3D would be 11.0 and RISAFloor would be 7.0. So we'll start out just taking a look directly at RISAFoundation, but then we'll also take a model from RISAFloor into RISA-3D and then into RISAFoundation. So it is kind of important to pay attention to the versioning of what you're using. So let's talk a little bit about what's kind of new in RISAFoundation. I know folks, maybe you're new to RISAFoundation, but if you've been using RISAFoundation, there are some new features we've added in the last version here. And I'd like to focus a little bit on these too, so if you haven't been familiar with them, we can see how to use those. So one of the big ones that we added was DXF Underlay. So we've always had DXF importing and exporting and things like that inside of RISA, but DXF Underlay works a little differently in where you can draw, bring in a DXF where you can draw to it. So instead of using a drawing grid or a project grid, we can have a DXF underneath and we can draw directly to the DXF. And this will be helpful if you already have your foundation plan drawn up and you want to just trace that drawing from your DXF. So I'll demonstrate this a little bit further in my model, but it's a great tool and it's actually available in all three programs, RISAFloor, RISA-3D, and RISAFoundation. So copy functionality was added. That's kind of something that's been in the other programs for a while, and we now have added into RISAFoundation, so you can copy different elements from one part of your model to another part of your model. So that's really helpful if you're doing very duplicate things in parts of the models. The other thing we've added is offsetting the slab. So that way you can just draw your model right around the exterior there, and you can just kind of offset it quickly. It's very easy to do that, and I'll show you how to do that as well. The other pieces here we've added is for applying loads. You can do a line horizontal force, and you can also apply a line moment into the program as a force. We added a pile cap editor, and I'll show you that. It's a little bit easier to see graphically what you're doing with your pile cap, and so now there's an editor for that. We have editors for some of the retaining walls and other functionality. It's nice to see that it's more graphical, and I'll show you that as we work through it. And then we added some new codes. We added some new Canadian codes for the retaining walls and also for the load combination generator. And so we'll kind of jump into that a little bit and see the different codes that are available in RISAFoundation. So let's see RISAFoundation in action. So let me open up RISAFoundation here, back behind it. So just starting out a new model in RISAFoundation, if you open up a brand new model, you get starting a model just like you would in RISA-3D, and this is just a kind of a quick tool to get you started. I'm going to close that, and I'm going to take a little perusal around the interface a little bit. So if we look at this in RISAFoundation, we see that we have all these icons, very similar to some of our other programs. One of the big ones that stands out here is the global icon, and I'm going to open that. You can either open it on the top or you can open up on looking at this globe. And this is sort of a good starting point for all models. You can go ahead and look at the description. You can enter in some of your name, your company name, what you're talking about in this model if you wanted to talk about the loading or what is happening, what portion of the structure, maybe some notes to yourself. That's a great starting spot. But solution is where I'd like to look at here. So if we pop to the Solution tab, I see here that I have the subgrade modulus and the allowable bearing. Now here is exactly where I'm going to be wanting to enter all the information in for my soil. This is the location that will be used for the entire model. Some folks use soil regions, but you don't need to use soil regions. You can just enter this in, set it right here, one spot for the entire model, and it will be and you'll just, at one location, this will be used for all your different elements, for your slabs, for your footings. Everything will be used based on these values right here. So if we look at the subgrade modulus, what that is, that you can typically find that on your geotech soils report. So that's a value here, kips per foot cubed. And then you'll also get, on that same soils report, you should get something like an allowable bearing. So you can adjust that. Let's just maybe give ourselves 4 kips per square foot. And the rest is some more analysis information, so we probably don't need to change those values right here. But we will go over to the Design tab and take a quick look at the codes that we have available. So if we look down here, we see that we have the ACI 318-2011, the most current code, and you can always go back in time and use some of the older versions. We have the Canadian codes here, so you have some other options for some foreign codes as well. So I'm going to stick with the most current version. I'm going to say OK. So let's kind of get started with what some of the different elements here in RISAFoundation are. First of all, we're looking at a two-dimensional view on the screen, and this is a plan view of my model. So if we look at this in isometric view, it's kind of tilted on its side. What's helpful for me is I always like to turn on my axis. I display the axis, and that makes it sort of familiar to me when I'm using RISA-3D, what I'm looking at here for the axis. Now, Y is going to be your default global vertical direction. So if we look at this axis on the left side, I see that X is in one direction, Z is in the other direction. If I go to plan view, X is my vertical direction in the screen, and Z is my horizontal direction. Now, coming off the page or towards me is my Y direction. So that's my vertical out of the page. So when I'm drawing this, this is how it's going to be. All my orientations are going to be globally to X and Z. So first I'm going to start by drawing a slab. So I'm going to click on Draw a Slab. And I want to draw a slab that's a little bit larger than what my grid has here. So I have a 30 by 30 grid. So in order to do that, I can do a couple different things. I'm going to actually change my drawing grid. So that'll be a little easier to do. So I'm going to close that and open up my drawing grid editor. And here I have the ability to put any kind of grid I need. This is by default, I mentioned 30 by 30, and I'm going to change it to be 50 by 30. So that means I can have a little bit wider slab there. So if I say 50 by 30, that just opens up, and in the Z direction I went by 50. Now, a note on the side here, you had radial grid opportunities to do a radial grid, so it would help you to do something on a radius, and then we'll go into DXF imports later, but you have some options here for creating your own grids, and if you do go ahead and create something very intricate, you can save that grid to pull up later. So I'm going to take a look and start drawing in here on this 50 by 30 grid. I'm going to draw that slab. Now, when I was in that draw slab here, you can see it has a material set. And so we have some default set materials for concrete. 3,000 normal weight, NW is indicating normal weight, 3,500, 4,000 now. When I worked in the field in concrete, these were kind of lower numbers. So what you might want to do if you're going to be doing some higher numbers than that for your concrete strength, you can go ahead and just add that to your material spreadsheet. So to add that, you just push enter, and then you go ahead and enter in all the values that you need there to create that. So for this demonstration, we'll just use our standard 3,000 normal weight, but you can create any of these different types of concrete, strengths that you need, change any of the values you need, and then if you do really work with values that are very different than what we have for defaults, what I recommend is pushing this default button at the top. It looks like a little disk, and you click on that, now the program will remember every time you open the program, it will use the values you choose in here. So I'm going to go ahead and draw that with a 3,000 normal weight, and I'll say that it's a 12-inch slab. When I'm drawing in slabs, I'm just drawing to this drawing grid, and I can draw wherever I want. So I get sort of this, you can see a rubber band command, and it allows me to draw whatever shape I need. So for example here, I'm just going to do like an L-shaped slab. So I'm going to go over here, and in that last click, if I wanted to finish this at this point, because I'm going to do it this L shape, I just click again at that point, and that finishes my slab draw. So this is a little funny, right? I drew that a little crooked. That's okay. I can draw it in this odd dimensions, but if I say, hey, that's not actually what I meant to do, I meant to have this be straight, what I can do is I can see that I wanted that actually to be in the Z direction of 11, or excuse me, the X direction of 11. So I'm going to go ahead and double click on that. Sorry, Z direction. So I'm going to double click on that node, and instead of being 12, I'm going to change that to be 11. And by just making that one change, I corrected the slab. So it's really easy to make changes to your slab by just changing the node instead of having to move things around. Okay, so I now have a slab in place, and we'll come back to adding loads to the slab. I want to kind of add some different elements into this model, and then we'll discuss loading after that. So the next step I want to do is go ahead and draw some retaining walls. So I'm going to create a retaining wall there. You see there's an icon. It looks like a blue icon. I click on that. and it allows me to pick my material set just like with slabs. I'm going to choose the 3,000 normal weight, and now it has a definition. And what the definition does is it defines all the parameters of this retaining wall. So I'm going to create a new definition here. If I look at this definition, we can see a little bit information about this retaining wall. The first tab in this is it's a graphical editor here. It helps us define what size and the geometry of it, so the sizing of our wall, and some general properties of this wall. First question asked, is this a propped wall or is it not a propped wall? And that's asking the question is there a floor framing in here that's going to help support this in the direction of that wall out of plane, or is it going to be just a freestanding wall? In our case, let's just leave it a freestanding wall. What wall thickness do we want to enter? So this has an 18-inch thickness. If I take a look here, I have the wall height being 14 feet. And then I see on the other side, the soil is actually going to be 12 feet up from that location. So measured from the same point, I have soil up 12 feet. I have ability to put a toe length as well as a heel length. So this one's a little unsymmetric, 3 foot in the toe, 4 foot in the heel. I can see that whether I tell the program that I'm going to be fully pouring that wall into the footing. So if it is fully connected, it would be yes, it would be monolithically poured. Otherwise, it's going to be connected, and how do I want to connect that? Do I want to connect it with a rough connection there or a smooth? That's going to change the values when we go to check that bearing and the connection right there. So we'll just say no rough, and then that'll be fine. We'll make that assumption. The dowels that you want to do, 1 or 2 layers into the footing. Now, if you need a key, that's where you can enter in this value. So first thing probably we'll do in most designs, you're going to probably start without a key unless you really know you need one. So we'll just say no key for now, and we'll see if it works without that. We can also tell the program if it's going to be restrained, and then it won't even check any of the sliding. If it's going to be restrained, we just say yes and then a key, or any of the sliding checks wouldn't matter. But we're going to say no, that it is actually not going to be restrained. The footing thickness we can define as well. So we'll pop over to the Soil tab, and in the Soil tab, we're going to define some of the information here. Now, this is all based on what properties you have. Again, you're going to pop into your geotechnical report, figure out what you have for your soil. You can put a surcharge right there. So we're going to have right now here a 500 pounds per square foot surcharge above that wall. We'll put an angle on that, maybe a 5-degree angle. So we'll see that they're actually going to be applied. The loads are going to come over and try to overturn this in a directional load. Now, if we leave we enter the gamma heel, and we enter in that, so that's going to be our unit weight. And if we enter in our angle of internal friction, those values there, if we entered these 2 values in for all of our different locations, so we're entering it in for the behind the wall, so that'll be our lateral pressure here behind the wall. And then if we entered in for the saturation point happens, so where your water height happens, and that would, again, if you remember from this side, you have a saturation height over here at 6 feet. Okay, so that's where that defines that water height. And then on the toe side. So you have the ability to change all of those different regions of types of soils. Now, if you leave that blank, that K there, if you leave that coefficient, we'll actually calculate it for you. We have some of those equations listed in here. So I'd just like to pop into the help and show you, if you do leave that blank, we are going to find your lateral force coefficient K based on some of these values you're entering in. And so that might be something you decide that you want to override. Otherwise, it's going to be the program will decide that K heel, the K saturation heel, or otherwise the K toe values. So if we see, we can enter all those in. And then on the rebar. So the last tab in that retaining wall is going to be pertaining to the rebar. Now, the rebar is handled in 2 different ways. So one is going to be that stem wall, and then the other one is going to be the footing. If we look at the stem wall, we have some choices here to make. Do we want to make it each face, single layer? If we make it single layer, that means that it warns us, hey, you have to have 1 dowel if you're only single layer. I'm going to go back to each face. Probably each face is more typical. I don't know what part of the country you're all coming from, but it depends on where you are and how much we're going to be worrying about things like frost or what kind of forces we have there. But I'm going to say each face for this one. Now we can tell the program the outer bars. In this drawing, we're drawing those outer bars where the vertical bar is on the outside. You can flip-flop that so it could be the horizontal bar. This bar will be on the outside of the wall, depending on what you need. Now that's going to change your D values, so that's kind of an important one to make a decision on if you're real tight with your design. We've got the external cover and the internal cover, oftentimes differing, so we can have the ability to do that. Now the program is just going to put the bars in here based on what we tell it. So we may want to choose some bars wisely, maybe number 5 for the horizontal bar at 18. We're using external and internal bars. I don't know, sometimes whenever I've worked with construction, I like to kind of keep these consistent. So I'm going to say not change it from the number 8 to number 7. So I'll have both the external and the internal bars be number 7, so I don't have any problems in the field worrying about what one bar size change. Maybe you need it later, but I always like to match those if you can. On the footing portion here, again, you have the same kind of choices where you want to put those bars, each face or a single layer. You can tell the program here. Now the footing is going to be actually going to be sized for you, so it's going to, the program is going to space those and then grow the spacing as needed per the demand. So we'll see here if we have, we're going to tell the program the size of the bar. Number 4 bars are the longitudinal bars, and the top bars here are number 6s, and the bottom bars are number 6s at the bottom. And the program will tell you, okay, between this minimum top bar spacing and the maximum top bar spacing, what was needed. Okay, same thing on the bottom. So it's going to size those for you. You're going to define the covers, of course, listed here, bottom cover and the top cover, and then go from there. So you have all of these definitions in place, and I can just say okay. You can pick one you've got there. We're using a number 3 from the list, and this is all available also in a spreadsheet. So if you ever want to pop back into the graphics, you can pop that open there, or you can go ahead and open up a spreadsheet, and it's also in a spreadsheet, kind of easy for you to use in a spreadsheet format as well. So let's draw this retaining wall. So when we go to draw this retaining wall, we're going to say apply and draw it. And I'm drawing it on the grid. I'm just going to draw that right there. And I see that it's drawn 2-dimensionally. But if I look at this in isometric view, I see that that is actually drawn physically off the page like that. And I see that it's a 3-dimensional item. Now it does, let me go back to that. It does, when I draw anything like loading, all of that is going to be on this plan view, but we'll see that the loads will kind of pop to the top when we look at it graphically, which is a nice way to see it. So let's go ahead and I'm going to go back to my wireframe, and let's go back to plan view so we can take a look at it. So once we have our retaining wall in place, let's go ahead and draw some other things. Let's draw our footings. So we did a retaining wall, we did some slabs. Now footings are available in what we call the support type. If we look here, we have the ability just to drop in some supports. Maybe something is externally supported. You might need to use a support like a boundary condition. But we also have footings in here. And I have a footing type listed here, footing type number 1. And I can just draw in a footing. Now this is a single node, and I just click on anywhere, and that single node will be drawn with a footing surrounding it. And that means that this is typically where you're going to be applying a column loading just to this single node location. If we look at what that footing definition means, let's open up that spreadsheet here. It's on our data entry toolbar. That footing definition, we have only one defined currently. So this footing definition, let me open that up, is telling us here a little bit of information about the minimum and maximum steel ratio that's required for this footing. The material, again, you have that laundry list of different types of materials you might want to use. We'll use the 3000. Now you have a design rule. This means that this is what is governing the design of this footing. In particular, in concrete, what we're talking about for design is specifically is the reinforcement. So we have a typical beam they're listed on that. We also have a typical column and typical slab. Let's actually create ourselves in this design rule a typical footing. So if we call this typical footing, I opened up a design rule. Everybody sees that design rule is listed right there, and we're opening up that. And we'll see the program will tell you here it gives us the maximum bending check and the maximum shear checks, and that means that if you don't want to run to the 100% of the capacity for your steel there, maybe what you do is you tell the program 0.9. I want to go to 0.9 for my max bending check and 0.9 for my max shear check. That means if maybe you don't know all of your loads yet, maybe this is just a preliminary preliminary design, and so you decide that I can't really run up to 100% of design yet capacity. Otherwise, later on when folks tell me I have higher loads, it won't be adequate. So let me design this to 90% and then go from there. You can define the cover listed here, top cover and bottom cover, and that's all your general tab. Now the only tab we're worried here is we're going to pop over to the tab that we're worried about, which is footings and pile caps here, and that's where we're going to tell the program what type of bars we should be using, top bars and bottom bars. Okay, so we're using number 6s on the top and number 6s on the bottom, and you can choose from any type of bar you want to use for that. So we'll just go over back to the design rule, and we'll say, okay, use that typical footing one we just defined with the 90%. The next column we define here in footings is whether we want equal bar spacing or if we want to band them together. So we'll say let's enforce equal bar spacing. The group design, so if I have a lot of different footings around our structure, I can tell the program that all of them should be grouped together and designed similarly. Otherwise, each one will be designed separately. And so typically I'm going to do separately, but if I decide in my next model where I have a whole group that are gravity and a whole group that are lateral, maybe I want them all to be grouped together so that they behave similarly and they are designed that way. It also can maybe make the difference for your construction so that you don't make mistakes in the field. Again, having all very similar footings might be easier for you to build once you get it out to the build stage. Concrete bearing, that's going to be telling the program whether we're doing a concrete bearing check and then whether we force top bars on that footing. So we'll just leave that force check turned off, and we're going to do our concrete bearing, so I want to review that when we look at the footing results. So geometry will come over there. Now, footings are actually going to be sized based on the demand. So whatever kind of loading you'll see on that, we're going to actually size the outer perimeter of that footing based on that demand. So we're going to say the minimums and maximum lengths as well as the widths. So the program is going to stage this from a 2-foot by 2-foot up to a 10-foot by 10-foot footing. You can increase that or decrease that. If you decide, hey, I already know what size I want. I specifically want a 4x4 footing. You can set the program to be 4x4, and that's just as easy as telling the program 4x4. Just a title maybe that we'll say set 4x4. So I give it a name that maybe means that. And I can tell the program here, give a maximum length of 4 and a minimum length of 4 and a max width of 4 and a minimum width of 4. And that way, now I'm not really doing a design on that there. I'm not sizing it up or down. I'm just checking what you already have told me I'm going to use there. And so that's all set up. So we've got here an increment. So if we are going between these sizes, we can increment this length to width ratio. How often do I want to go? So I'm going to start at 2 and then move up by half a foot. So 2.5, then 3, 3.5, and etc. Again, the same thing for thickness. We're sizing that thickness from a minimum to a maximum in here. Same thing, you can set this to be, if I know I just really want to check a 12 by 12 inch thickness, I can just set that to be the equal numbers and it will use that. And the same kind of increment. We can move up by 1 inch from there. So 12 inch, 13 inch, 14 inch, it will size up. Now, I can also force these footings to be square if they need to be. The pedestal is an input value. You just tell the program, hey, what is that pedestal? It's a 12 by 12 by default, kind of a nice default setting here with a 24-inch height. You can also do some things like setting an eccentric. I like to sort of demonstrate this. If you have an eccentric footing, you might set this up to be a 12 by 12, but it's offset by 12 inches in both directions. So when you draw it, we'll see that that's actually going to be offset. You can also use a boundary type condition. So that boundary would be something like if you're up against a property line and you want to grow that in 2 different directions, you can set your boundary up there. If I look at the soil conditions here, we can tell the program some things about overburden. So that's the weight of the soil above the footing. If we want to have any passive soil resistance to sliding, we can put a value there. And then we tell the program what the friction of coefficient there for sliding once we do that. We also here use the gross properties for this soil above that we're defining there. So we're going to say this is going to be the gross properties. So I'm going to go ahead and I'm going to close that down. I'm going to draw a footing in. using that eccentric one I defined. So I'm going to tell the program here, use the eccentric, and you can see it's just it's offsetting that by 12 inches in both directions from the center line. So if we looked over it by 12 inches this direction and 12 inches this direction, I'm up by that direction there. And it will size around that offset. And the other thing you can do is just take a look at that 4x4 that I created, and I can add a 4x4 footing. So now it's not going to size at all. It's just going to check that one. So you have some different options for your footings. Again, though, this is just for a point load, so we're not going to be doing a combined footing in this manner. It's just going to be a single point load on that. Actually, any different types of point loads, but it has to be a point load. What I'm going to do next is talk a little bit about piles. So piles, there's two types of things when we talk about piles themselves and pile caps. So let's see, we have with piles, we have two types of piles available in our default settings, and let's take a look at what a pile is. So if we close this up and I open up my pile definitions, really, what are piles? Piles are used when you have soil conditions where you need a little bit extra depth in there and you're trying to use a pile to help support your slab or footing or pile cap, for example, which is very close to what a footing might think of if you think of a footing. So what we look at with these piles, we have the ability to change their shape, so they can be either round or square, and we have two default settings for these, round and square. You can change their diameter or their width around, so the side dimension there. The pile embedment, how embedded that is into the cap or into the slab. Now, if you look over to the next options here, is what that pile is doing in relation to what it's connected to. First of all, it's considered a spring type or a boundary condition in the slab or in the pile cap. So what we want to know is what its capacity is for taking compression, for taking shear, and then if it can accept any tensile or uplift loading. So our default has the program allowing no uplift in this pile, which is kind of a common occurrence, but maybe yours has a special case where you can allow a tensile, so you can add a new type in there. But the other kind is that you can set these capacities, and beyond the capacity, we also need to tell the program is what is this pile doing? Is it a fully rigid an element here, like a boundary condition element? And if so, we just type in rigid. If it has no capacity in that direction, like the tensile, it would be 0. So we're saying that it has no stiffness in the tensile direction. But in the shear direction, we're saying it also is fully rigid. If you want to tell the program here, you could give the program, instead of rigid, you can say it has some kind of a spring constant capacity here for stiffness. So if we say 100 kips per inch, that would be your compressive stiffness in that direction, and that would act more like a spring than a fully rigid boundary condition. And you can choose the different directions. Maybe you're going to give it maybe 10 kips per inch. I'm making these numbers up, but these would be numbers that you would actually look into seeing what your actual pile has capacity. Okay, so you have the ability to draw these. Now piles, the way we're talking about these, are just single entities underneath a slab. So let's look at, I'm going to draw some in and so we can have an idea of what these look like on our model. So if I draw piles, I'm going to go back to assigning a boundary, a support type, and I say apply, and it would be underneath a slab. So we see if we click on these couple different of these drawing grid points, I can see I can draw them in as round piles like that. I can do as my second type there with my square, and it will graphically show up as a square on my screen. So I can support maybe just as for example, I'm just supporting this portion of my slab on piles. The rest of the slab is just going to be slab on grade based on the subgrade modulus n that I've defined previously. So I've got piles in my model. I've got now what the question is what is a pile cap versus what is a pile? Now a pile is supported underneath that slab, and let's just look at that graphically on our screen. So if we looked at our slab now, we can animate this slightly and just see that we have a pile cap. I'm going to try to show you this a little bit here. I'll turn this up a little. My mouse makes it a little hard to see here, but you can see this has got pile cap, that these piles are directly under our slab. Now a pile cap is going to be slightly different in where it has a set geometry. So if I pop into the pile cap, I can open up this editor and I can take a look, and this is a brand new feature I mentioned. It helps us see what the pile cap looks like. A pile cap really is just a thickened slab region with a grouping of piles underneath it and a single node in the middle under a pedestal there. So You have some different formats. Here you can see what a 2-pile looks like, a 3-pile, and these are just some standard formats for pile caps. In our model here, we'll just maybe pick a 6-pile. I can tell the program here what type of pile to put underneath it. So in here we've got this pile cap has 6 piles, and it can be either the square pile type or that round pile type, or it can, and whatever properties I defined in those, we'll just keep it as that round one we just said. The spacing of those piles will be defined based on this factor I enter in. So if I know I have 6 piles, but how big is this pile cap is based on how big I space these out. The edge distance required, so now I have 15 inches off this edge, which is coming off, you can see off this diagram, off the center line of that pile to the edge of the pile cap. And then the thickness of the pile cap, you tell the program here, since they're all grouped together closely, there's sometimes do a reduction factor for either the axial or the shear. And then we can do some just general what type is the minimum and maximum steel ratios that we're going to be using, the type of material, if there's an overburden, and then the pedestal information. So you set all these up and you can just say okay, and you can start drawing this just like we drew a footing. It's a single node. So if I pop that in there, you can see it's a single node. That would be where you'd be applying your point load on that single node location. So if we look at this here in wireframe view, we see those 6 piles that we had underneath that. So you've got your pile caps, you've got your pile, all your footings in place. Now let's talk a little bit about the loading aspects here in RISAFoundation. So you can draw in loads on your structure using the tools here. There's some icons. I'm going to do some point loads because that's kind of the first and foremost. You can draw in a point load, and we can tell the program the category we're going to be using. So I'll just be using dead load here for example purposes, but you want to, if you're going to break down all the different types of loads you're going to be doing, you can do it in wind loads and seismic loads. And when we see the model come from RISA Floor into RISA-3D, into RISAFoundation, all of those loads will be categorized for us. It's really nice. It does that really quickly for you. So here I'm going to just tell the program I'm going to be using 5 kips, and the direction is important. So the Y we said was going to be downward, and it's going to be on our model is a positive is downward. And this is just a quick, easy way. This is the opposite of what's in RISA-3D. In RISA-3D, you would have always said -5 here. It's important to note that since it's always going to be typically down, most loads are downward in RISAFoundation. Occasionally you'll have upward loads, then you would put a negative there if it was upward. But here it's downward for the most times, so we'll always sort of use that +5 for the downward or whatever direction, the quantity you're using. You can also put moments in there, or we're going to just using the X here, excuse me, the Y direction. So if I say apply, I want to put that load on top of these footings. And as I mentioned, this is a load on a footing. If I decide to put this load out here, that it will not go into the footing. It has to be on the footing pedestal in order to be a part of that footing. If you have a case where you have a footing that has loads sprinkled all around it, not on the pedestal, then you would be using a slab, and you can draw in pedestals on top of a slab to do that. But I'm going to just go ahead and delete that or undo. Well, undo button is really helpful if you make mistakes like that. And I'm going to put that on my pile cap. And now also I can put that right on my retaining wall. Retaining walls can get line loads or point loads. It's up to you here. You can draw them in, and let's take a look. When I mentioned that when you draw that point load at that location, a node shows up at the bottom, but graphically it shows up at the top of that wall. So actually we're pulling that 5 kips through the entire stem wall. Okay, so if we go look back at that in plan view, we see that there. You may want to go ahead and also put some point loads on your slab. You can put point loads anywhere on your slab. Maybe we have some sprinkled around some point loads over there. You can also go ahead and do line loads. Now line loads here, if we click on line loads, you can see they can be the same types of categories. We can tell the program here that it's going to be maybe 5 kips per running foot. Maybe that's a little large. Let's just say 1 kip per running foot. And I can say, that, again, that's a positive direction. It notes it here just in case you forgot. Positive means downward. And I can say apply, and I can draw that on top of my retaining wall. When I draw it on the retaining wall, again, you can note it goes to the top of the retaining wall. And I can maybe put it anywhere on my slab. So a line load would go anywhere on a slab. Maybe it would, for a wall, for whatever you're trying to demonstrate as a line load. If you look at, again, those footings, I wouldn't want to put line loads on that. Then the last type of loading I would be doing would be area loading. So I'm going to go ahead and open up this draw area loads, and area loads would be something I can do on a full area. Let's just say maybe 0.1, which is 100 pounds per square foot. Maybe we'll do this one as a live load, and I can draw that anywhere. An area load can be any shape, so I'll probably just follow the entire slab, and I can draw around the perimeter there, and I'll see that in a graphical view here, showing me what's the view here. Now, if you're using this between different types of loadings, it's really helpful to go look at your different types of loading and just drop down this list at the top. Dead load is displayed currently, and then we can see live load that I just applied as an area load. If you have any other types of loading, earthquake loading, it's real helpful to toggle through this list and see how that happens. You can also use a load combination view. So if you click on this on the right, you'll see it turns from being a category viewing to a load combination view. So we see that there's service load there, and then there's the strength load, and it's being increased by the load factors. So you've got all your loading in place. You've got one last piece of this I wanted to demonstrate was we have a slab generator for a circular slab. So if I click on that, I can see that right next to the slab drawing tool, there's a create a new model from a template, which is a circular slab generator. And this really helps us quickly draw a circle of a slab. It also helps us do the donut, which is kind of what I wanted to demonstrate today, because it's a more complex way to draw is using a donut type tool. So if we look here, I'm going to just put a polar origin. So this is going to go, I'm just going to pop this at the top of my structure. So I'm going to say that this is going to be 50 feet above the structure I have currently in the X direction and maybe 25 feet. So that's going to be where its origin is. And I'm going to give it a radius of 20 feet. So the inner radius, though, I want it to be a donut, as I mentioned. So the inner radius is going to be 5, and the outer radius is going to be 20. So that means I'm going to have, an inside opening in this donut type shape. The thickness I'll leave at 12 inches. I could set the material set. I'll again leave it at 3,000. What's also really powerful in this is I can set up some loading. So I can do some line loading in this. The first option here gives me, again, an ability to do the category of the loading type. I'm going to tell the program it's going to just be maybe 1 kips per running foot. And the radius now, I don't want to do 3 feet there. I'm going to get it onto my slab in my donut here, and I'm going to say it's going to be maybe 8 feet. So if you remember there, look, I have 5 feet in the inner hole. So I'm going to say the first radius for line loading is going to be 8 feet in. You can also do things like the area loading. I can area load a whole section. So maybe from 10 feet to 20 feet, I have a whole area load. So for inner radius of 10 feet over to 20 feet, I'm going to tell the program that I'm going to be doing 0.1 kips per square foot or 100 pounds per square foot in the dead load case. So if I say OK, and it will automatically put my design strips in for me. I'm going to zoom out here. We haven't hit on design strips yet, but I'm going to zoom out a little bit. And I can see, let's unselect our whole model and just select this portion so we can really focus in on what's happening in here. If you just select that portion and look at this in isometric view, you can see here that's my area loading around that. I have my center loading and that line load that went into the center of that donut. And if we turn off our load so we can just see, okay, then we get to see that this is the slab we talked about on the perimeter here. And on top of that slab has some design strips. So we can see there's some design strips on that. Now, I didn't mention design strips yet, but let's talk about that farther. So design strips, we have drawn a slab edge around the perimeter, and the slab we've defined so far knows about its thickness. We can look at that here. It knows the thickness, and it knows the concrete that it's using. But it doesn't really know anything else about what I want for reinforcement yet. And that's how it's handled separately with what we call design strips. The reason why you might change design strips within a slab, rules might change, but what a design strip is, it's just an area over which we're going to be designing that reinforcement of. So I'm going to take a look at our design rules, and we'll pop over there because that's where we define our design strips in our slab tab here. In the slab tab, we see that I have a different reinforcement here. It's top bars and bottom bars, and then we have the size of the bars. Top bars are going to be here. So we're going to use this typical slab definition, and we're going to say that this top bar, let's change it to number 6 bars, and we'll leave number 8 bars for the bottom. We can tell the program the maximum top bar spacing and the minimum top bar spacing, and again for the maximum and the minimum for the bottom. Just as I mentioned earlier, if you decide you're doing more of an analysis of an as-built or a situation you already know, you can set these values to be equal, and then you'll be checking what you currently have. So we'll let the program design this for us, though. So we have an 18-inch and a 3-inch. It's going to space the bars from all the way from 18 all the way down to 3 as needed. You can tell the program how fast to increment those bars. Sometimes 2 inches is adequate, but maybe in a case where you're real specific about what's happening there, you might want to knock that down to 1 inch so that we don't go from 18 down to 16. Maybe we go from 18 to 17 to 16. So you might want to tighten up that increment. Rare that you need to go to that level, but sometimes that could happen. Side cover, so at the side of each strip, we know about top cover and bottom cover, but the side of each strip, if we want to have a little bit of a gap so we don't just lay your first piece of reinforcement out there, we might want to put a cover. But we leave this typically as 0, and we see what we need to do to fill in. But if there's a condition you need to actually bump the side so you have no reinforcement on that side, you can do that. And now rebar options, and this is a question I had recently. Can you tell the program to do just bottom bars? Well, you can if it's needed. The way you tell the program just do bottom bars is to say optimize. If it does require top bars, then you will get top bars as well. But if you only need bottom bars, and we'll see that in a common case here coming up in another model, where we only need bottom bars, you can say optimize, and you should only see those bottom bars. Mid-depth only, we'll set that only at that mid-depth, and then we can also always force top and bottom, but we'll just leave this as optimize. So what's interesting about design strips is it can be placed before or after you run the analysis. I actually don't really have a preference, so I sort of go with that. We can always go just draw them in right now. So we can go ahead and say draw strips. And when you draw that, you need to tell the program your rebar orientation. Are you trying to orient them vertically or horizontally across your screen? So we're always kind of thinking horizontally is going to be across the screen in this direction, in the Z direction here, and then vertically is in the X direction. Or you can also do them at an angle. So for this slab, for this one right here I'm looking at, I'm going to say it's going to be going vertically, or we'll start with horizontally. And I can tell the program I want to use design slab, typical slab design rule here. And then how many cuts. Let's get back to cuts after a second here, but I'll show you. I'm going to say apply. I'm going to draw this in. I'm going to go across this lower portion. So what I'm really doing is I'm telling the program this is a whole region that I want to design similarly. I'm going to be cutting across this whole region, and this is what I want to design all the reinforcement in this area the same way. I'm going to be doing it in both directions, horizontal and in vertical direction in the same area. So I'll go here and here and here. Okay, so now this area I'm going to be doing it this way. I am also going to be going up here. I'm going to draw in some design strips here. So I'm going to go and say the design strip in this direction would be similar, and I'm going to go and do another one in the horizontal direction. So I draw this design strip over this region, okay? So now I see that there's little red lines there in either direction. Okay, so now I have all of my model laid out. I'm going to go to load combinations, and I have some load combinations started for me. I'm going to go ahead and run the batch solution. And in RISAFoundation, it always runs a solution between the batch. So it tells you that it goes through each single combination and finds a solution, and then what we do is actually for reinforcement, we're enveloping the reinforcement, making sure that we're hitting for everything needed in there. In this case, I'm only using 2 load combinations, so it's pretty simple. Once we've solved the model, first thing we get to see right off the bat is that slab information. And we see that I get reinforcement in the slab. It's showing right on the page, which is really helpful to see. And I get to see I'm using 18 spacing there, number 8s on the bottom, and number 6 is at 18 on the top. In this direction, I only needed number 8's at 18 on the bottom. And learn a little bit more about how that design gets done. Let's take a click at the detail report. If I click on detail and I click on the actual reinforcement design rule there, I can click on the reinforcement name, I pop up open the detail report for the design strip. So in this design strip, if we see it, we're looking at only, this is design strip 4, and in design strip 4 we see moment only on the bottom. and it tells us here it's specifically all the information for this reinforcement, the total number of cuts. Now what's happening internally is that the program is making internal cuts across this one. So this is actually, let's see here, and I'm going to show us a little. It's hard. Let's see. Okay, so this one is this directional design cut. Internally, this design strip, is got cuts internally in it. And I'm going to show you that on the screen so we understand a little bit farther about what's happening with design cuts. So if I look at this on the screen, what we're doing internally is we're taking 50 cuts across this design strip. Each one of these cuts is going to be determining what's happening inside there, and we're getting a code check on that. And we can see the label of each one of these cuts. So if we zoom in, we see DS4, which indicates that that's design strip 4. We have a cut labeling from 1 all the way up to 50. So if I zoom out a little bit and I go look at that detail report again of that design cut, or design region, I'm going to click right there. We can see in this design strip for this design strip region here, it tells us a little bit more information about what was the code check and what governed. And so the top check, there is no top bending, so we have zeros throughout there. The bottom check, it tells us DS4 X35 was the governing cut, and that's what the cut moment was found at that location. And then we also see on shear, we have a one-way shear check, and DS4 X21 was another location or another cut which governed us for that cut. To find out more about why that happens that way, you can go ahead and see below here. You can click on this Design Cut 35, or you can just pop to the top of this and say Design Cuts. Click on that, and it will pop to the governing one, which is DS4-X35, and it tells us here specifically why this one had that many, what the forces were in that design cut, and why it was reinforced in that way. So top bars required, it tells us the amount of steel, temperature, and shrinkage, and what was provided. So we get to see how much was provided versus what was required. So if I can go back to the strip and I can take a look. So if I want to go to X21, for example, I can pop over to X21 using the arrow keys to see why the one-way shear was picked as the highest code check there, or I can go ahead and maybe click on that cut. Now clicking on the cut, I just zoom right in there and click on that itself right there. So this gives us kind of a view. A lot of times in reinforcement, temperature and shrinkage is probably what's controlling things. So sometimes it's a real close call about what might be controlling. But if we see on the screen here, this kind of helps us sort of understand and break down all of what is happening in this reinforcement and take a lot of the mystery away. But a big clue to this is that a lot of times it's just the minimums that required are forcing things to happen. But I'm going to kind of turn off some of these labels because they're a little hard to see. The next thing I can do is take a look at maybe my retaining wall. Let's look at a retaining wall because that's an interesting report to see. If we look at that retaining wall, we see that I have just a sketch detail report telling me what was in the retaining wall when we entered it in. Below that, I see the loading diagram. I can see that loads got broken down into each piece here. So I had from the soil, from the surcharge. I have that surcharge is broken down into a little bit of axial as well as horizontal. I get the soil loading all around from all of the different pieces. And then I break it down and goes into what the geometry and the materials are. So a lot of this was data entry that you entered in, but it does give you this information. So if you had to do a calculation, you'd be able to know that. And as you scroll down below that, we get to see some of the information inside of that wall. So you see the axial loads here, the shear, and the moment, as well as the code check information. So because we're using interior and exterior, it's going to be broken down kind of separately. So if you see that you have interior moment versus your exterior moment listed here. Now, one piece is there is a threshold. So I always like to point this out because it's a little, this is kind of a piece of the code that if you're not familiar with, you forget what happens here. So I'm going to just point out this little piece here. So scrolling down into the help, hold on, we'll bump to this threshold. So what I'm also seeing is there's a lot of information inside of this in the help file. So if you ever get confused about what you're looking at, what the program is doing inside of here, it's really helpful for you to pop into this help file and see what might be happening. So if we look here at this equation right here, I see that the moment and axial force thresholds. So if the program finds that the axial is smaller than this, we see that PU here is going to be smaller than this threshold, then it's going to actually zero it out and ignore it. Same thing can happen for moment. So if you ever find in here that you say, hey gosh, that says 0, but I see that it says shows axial, probably we're underneath that threshold. In this case, we can see that 5.9. If I jump over to the service level here, I can see that 5.9 was governing in the exterior portion, and then the interior portion of that reinforcement, it was actually the moment that's governing here, so that this threshold wasn't met for the axial. So with more realistic loading, you might find that this doesn't happen as often, but if you ever do see that, that's kind of a good clue. You can see that the area of steel provided versus the area of steel required. Again, a lot of times minimums are controlling these steel reinforcements. So you can see here, the footing design that I did not meet the minimum temperature and shrinkage. So it's giving me a big warning there, and I would have to go back and increase that to meet this temperature and shrinkage. If we scroll down below that, I see the bottom bars in there. It gives me the moment, gives me the area of steel, and as well as giving me all of my shear in my top and my bottom of my footing. For the shear, for the heel and for the toe. There's an overturning check that's done. It's telling me here that my safety factor is 1.5. I'm getting a minimum of that. I am also, though, here on my sliding check, I'm exceeding my safety factor. So it looks like that's red. So I may need to go back and work on putting a key in place there. So that would be something I would increase, go back and design that with a key, and that would probably get me better in my sliding check. My soil bearing check here, again, is shown here under my unity check is under 1, so it's not going to be, so that's all okay. So the retaining wall is nicely in, I love to see it in the detail report because of the pictures and because it's very, very evident with my loading diagrams what's happening. But all the results are also in spreadsheet format. So you can always take a look at your results toolbar, which is floating around on the right side. The retaining wall results are listed here. We can go into each different capacity, the wall, the capacity. So very, very similar information with your detail report, except that a little bit more condensed and quickly and easy to attain. So that red number we saw with a 1.641 is listed right there, and we would see that really fast in the retaining wall report. It's kind of easy to see it that way. The other thing, let's take a look at our pile cap, and then I want to open up RISA Floor, and we'll review our footings and things in that and going in for RISA Floor and RISA-3D. So pile caps are very similar to footings except sort of reversed here. They're supported by our piles, and we see that in our pile cap report. It's giving us information based on the details of looking just on it as a plan view or the elevation. We see the number of bars that are placed in this. We're looking at number 6 bars at 9 inches on center, and as I scroll down below that, it breaks down the geometry. It does a pile cap capacity check. Now, not a lot was going on in this pile cap, so we're only really checking a little bit of axial. I didn't really apply too many loads in either direction. But it will check the flexural design there based on that, the top bar and the bottom bars based on the loading you applied there, and the minimums required, as well as the pedestal punching shear, and then shear check listed there. So that's coming from both sides for the pile punching shear as well as the pedestal. So you're thinking about a pile cap, you've got loads coming in and punching shear issues coming from both sides, the pedestal itself as well as the piles punching through. And it gives us some of the breakdown of how that punching shear was calculated for the pedestal as well as for those piles. And then since pile caps are going to be considered more of a deeper one-way shear check, a deep beam would be considered here. It's a little different than any other type of materials here, or items in RISAFoundation. And lastly, we're going to do some pedestal design on that and make sure we have enough reinforcement inside of that pedestal. So because it's a column type of there, so you see that. If we close that down, so the footings are similar. Let's take a quick perusal before we pump out of there. Here, footings are very similar information. You get to see those footings. They are sized very similarly as a pile cap. You get to see them in plan and in an elevation view. And as you scroll down, now the one thing is a footing is on the soil, so we're worried more about the soil bearing. And we're seeing exactly what that soil bearing and what capacities are there. And as you scroll down, you see the same type of flexural design inside that footing with the shear check, the pedestal design. We design those footings for overturning turning as well as for sliding. So you see that, and that's doing a punching shear check, or excuse me, a concrete bearing check there as well. So all of these values are also, as we mentioned in the retaining walls, are also available inside of our results. So you can take a look at it in a spreadsheet format, footing results. You can see that we see our footing in here, our steel, our footing code checks. All of that is right there for you. Just as easy as we saw it. The detail report's a lot more information. Okay, so now we've kind of closed out. I'm going to close out RISA Foundation, and then I want to jump into RISA, going straight through from RISA-3D and RISAFloor. So if I open up RISA Floor, for example here, I'm going to open up RISA Floor model. And this is a great way to build your model is RISA Floor and then take it to RISA-3D. RISA Floor, if you're not familiar with it, is a full building model design. So we just have a three-dimensional model here in RISA Floor that I built. It's basically just sort of a steel model on top, a concrete walls on the bottom. I put some concrete frames underneath there, but really it's just a three-dimensional model at the end of the day that's carrying all of our gravity loads down our structure. With a solution present, I'm going to take it over to RISA-3D, and I can see in RISA-3D, it's going to be applying all the lateral loads. So the wind loading is done here as you move from RISAFloor over to RISA-3D, and the seismic loading is done all in RISA-3D here as well. And we now have just the lateral portion of the model. So I have to, so once you have a model here in RISA-3D, you can solve this model, and this is just as if you could start a model in RISA-3D and do the same thing. Start in RISA-3D and use the director button at the top right corner with a solution present. So the only pieces you need to worry about if you build a model here in RISA-3D by itself, or if you build a model in RISAFloor going to RISA-3D, this is all automated for you, but you'll want to use these categories. It's very important that you define categories. RISAFloor and RISA-3D have categories available for the loading type. Now, RISA Foundation cares about what type of loading it is. Since we're doing service loads and strength loads, we need to know what are we doing for that? Is it a dead load? Is it a live load? This is all pretty important stuff for RISA Foundation to know how to design. So in that means that you have to be putting those categories in place here. When you build a model from scratch in RISA-3D, you can leave off your categories. RISAFloor will have a problem with that. Excuse me, RISA Foundation will have a problem with that. So you want to make sure you do that properly. And you can, once you do also have your categories defined, it's really nice because you can use your load combination generator and things will be automated for you to create those load combinations once you have those categories. Now, a quick tip if you're using RISAFloor 3D going into RISA Foundation, you only need to solve a single load combination, and the program will go through and solve all of the different categories for you behind the scenes. So that's a real time saver if you have like hundreds of load combinations, which can be common in bigger models. You can just run a single load combination with one single combination solution present there. I can go ahead and go use that director button at the top right corner to get into RISA Foundation. So it solves, and you can see it brings across every single load I had from RISAFloor to RISA Foundation. And what's great is now it's categorizing them for me. So live loads, dead loads, earthquake loads, any loading I brought across. Earthquake in our case was WLX direction or ELX or Z direction. All of that information was brought across for us. This is really detailed as we go across there. So when it's connected like that too, what's really nice is that if you make changes to your RISAFloor model or your RISA-3D model, all those loads will be taken across for you, and they'll be adjusted as you move into RISA Foundation. In this model, this came from RISAFloor. All the gravity loads are here, as well as the lateral loads that came from RISA-3D. So you see all of the different loading from RISAFloor as well as RISA-3D, and they're automatically in the model. One thing I want to show you guys is how to do the DXF import or underlay. So as opposed to using the file import or export, what we're going to do is use it under this drawing grid. If you click on the drawing grid, and you go to import DXF, we see that import DXF here is listed on there, and I can find a file, a DXF file. in order to underlay underneath this model. So I can tell the program some different information about where its origin is. I can say what the scale factors are, what plane to bring it in from. If it's a circle, I have different increments for incrementing that angle. If I have any arcs or circles. I'm going to pop open here a model I created for this. So I'm going to say it's going to be a DXF here, and I'm going to find it. It can import different layers. I'm going to let the program say use all of the layers I have available. Say done, and it's kind of laying out behind there. Now, sometimes this is hard to see, so I'm going to zoom in a little bit, and you can see I have a gray outline in behind that, which means that that's a drawing grid type of outline I can draw to it. So for this wall, I can draw this is a wall in RISAFloor and RISA-3D. I can draw a foundation here directly underneath that. So I'm going to do a strip footing underneath that wall, and if I draw that, I can just say by drawing slabs, I can draw that directly by clicking to this already. So this is assumed that I went in and did a foundation plan in a drawing prior to opening this model. So I'm going to go ahead and do that all around here, kind of outline my walls, and we'll kind of get some of these in place. And in this area, maybe I want to do kind of a smaller portion of that. I'm going to break it down a little bit differently. I'm going to say this is going to be like a little portion here, and we can go ahead and do just sort of smaller smaller foundations right around this area. And let's go ahead and draw some more slabs. Okay. So I've got some slabs here. Now in the center area, I didn't really go ahead, and I don't have this drawn out, but one of the tools I have now is I can draw a slab directly to the nodes. So I know that I want to have a kind of a mat underneath my elevator bay and some of these outer perimeter columns. But that's just not realistic to draw a slab exactly to the location of a point load. That would, fail obviously because it's punching shears and it's just not really, realistic. But what you can do is it's easy to draw that and then use our offset slab tool. So if I go over to offset slab, I can tell the program that I want to offset the slab by 3 feet. And I can say apply and now click on it, and it will offset that by 3 feet in the perimeter, which is really helpful for drawing around some different point loads. The other thing we can do is add an opening inside of that. Oftentimes in elevator bays, you're going to have an opening. And I can go ahead and instead of offset, when I'm drawing tab a slab, I can click on opening here. I can create an opening using a rectangular opening, and I can tell the program just to, let me zoom in here, and create a little opening right in here. So now in the slab, it's offset, and it's got an opening inside of it. So we've got some tools in there to do some different types of things in there. What you'd also maybe want to do is run around and put some footings in place. So all of these other columns, now these were lateral columns. It's hard to remember what my layout looks like, but these outside ones, you can see there's moment in them. Even for just dead loads, I'm seeing some different things here. So those ones, if we looked at WLX, we can see that there's some forces in that. What I typically would do maybe is, as I mentioned, have some lateral footings versus some gravity footings. So I can go ahead and go into my footing definitions, and I can call these lateral, and I can also do gravity. And so here, I'm going to force these all to be the similar groupings. So I'm going to say, hey, all the lateral ones, make them the same, because I want to have some similar footings, and that way it's quickly and easily to say, okay, under all those moment frames, those are going to be those lateral footings. The rest, just make those all the same. So we can, when we're drawing our footing, we can say, okay, just these will be the lateral ones, and I can box that area, and that will be showing up like that. And now for the other ones, I'm going to switch to the gravity ones, and these are going to be all footings in the area here. So I can and what's nice is it's really easy to draw footings. You just kind of rubber band your model around here. Now in this area, I have 2 footings that are together, and for some reason, I really want to combine these 2. And this is what I want to be a combined footing versus a single footing like that. And in that case, I can draw a slab instead of doing that. So maybe I'll do a 18-inch slab in this area, and I want to draw it. I'm going to go ahead and draw it directly around these 2 footings. And you'll see there's loads coming down on those. And So let's go to our wind loads, our dead loads again, so we can just verify, yep, those were where I wanted to have this combined footing. And in the combined footing, what I can do is I can put pedestals in place. So if I go back to draw pedestals, I have a choice here. Now this is meant for slabs, so you can draw pedestals on top of slabs, and I can tell the program here, a 12 by 12 sounds like what I had for the rest of all my other footings, so that would be what I probably would do. Maybe a 24-inch height above the top of the slab, and I can tell the program here I'm going to be drawing a pedestal right there. So now I'm doing a combined footing. This is going to be acting just like the footing is. The only difference here is that I'm going to be putting pedestals on it manually, and I would size it bigger or thicker manually. Slabs aren't typically bumped out in size because that wouldn't be something you'd want a computer program to decide for you. So you've got all of that different information. Because this came over from RISA Floor, I mentioned that you have all of those different categories, and you can see them listed out: dead load, live load, earthquake load, all of that broken out for you. So it's really categorized and well for you. But what is nice, too, is that you can use your load combination generator. So you're not going to just design for just dead load and live load at this point. You're going to actually go ahead and use that load combination generator. So opening up the load combination spreadsheet, the load combination generator is a big red label up there. You can tell the program to run the X and the Z directional and say generate and go from there. So you have a laundry list of different load combinations using all of the different types of loading that you had incorporated in your model in RISA Floor and RISA-3D, and run the analysis. Now you'd also want to go ahead and do your design strips around here. So you'd want to draw in those design strips for your slabs, and then you can run your analysis. As we've run out of time, I didn't want to go back here. I'm going to just jump back to our slideshow here and just talk about some additional resources that you might need. So I mentioned all the new features. Those are listed in our release notes, so you always can pop into that and see. Also on our RISA News blog, you can see that we have lots of articles describing how to use RISA Foundation, different aspects. It's a lot to cover in 1 hour, but each feature sometimes you can want to know more about it. You can always go into into RISA News to find articles written about it. You can contact us at support@risa.com. We have user's guides. So the first step whenever you're opening up RISA Foundation or any of our programs, we have user's guides that will walk you through a step-by-step tutorial, and I would recommend that as a step to go from there. And I'll hand this back over to Amber. Thank you so much for attending today.
Thank you, everyone, for participating in today's webinar, Learning to Use RISA Foundation.